Today we're going to be talking about electrochemical cells, but before we do that, let's talk about oxidation reduction reactions in general, because those are the type of reactions that are occurring in these cells. Remember, we call these redox reactions, and we remember the process going on in oxidation reduction reactions by the term oil rig. Oil rig helps us remember that oxidation is loss of electrons, reduction is gain of electrons. Oxidation and reduction, remember, always occurs simultaneously. You can't have one without the other. In order for something to gain electrons, something has to lose electrons and vice versa. So in the system, we're always going to have something that's undergoing oxidation. Remember, that's a loss of electrons. In oxidation reactions, when something's oxidizing, the oxidation number is going to rise and it's going to become more positive. Whereas in reduction, the substance that's being reduced is going to gain electrons. Since it gains those negative electrons, the oxidation number lowers and becomes more negative. We also have the terms oxidizing agent and reducing agent. Those substances simply refer to substances that cause something else to be oxidized, and something that causes something else to be reduced. Now, we're not talking about different kinds of substances here. The oxidizing agent is actually the substance that's being reduced. The reducing agent is actually the substance that is being oxidized. When we look at a balancing a redox reaction, remember the most common way to do that is with half reactions. The first thing we want to do is to find the substance that's being oxidized and the substance that's being reduced. So aluminum is changing from a 0 charge to a 3+ charge. So that's the substance that's being oxidized. We denote that with an arrow up above the reaction. And we use an arrow below the reaction to show the substance that's being reduced. The tin 4+ ion is reducing down to tin with a 0 charge, metallic tin. So in this particular situation, we could say that aluminum is the substance being oxidized, which means that it is the reducing agent. We can say that SN4+ is the substance being reduced, and therefore it is the oxidizing agent. So the half reactions will simply be showing that aluminum with a 0 charge, sometimes it's shown with that 0, is reacting to form aluminum with a 3+ charge. And when it does that, remember, when it's oxidizing, oxidation is loss of electrons, so we're going to be giving off 3 electrons. On the other hand, tin 4, the tin 4+ ion, is reacting to form the tin 0 metallic tin atom, and in the process it's going to require 4 electrons to do that. Notice that the charges on each side are balanced. We have 3 positives and 3 negatives here, which balances out with the 0 on the other side. We have 4 positives and 4 negatives here, which balances out with a 0 on the other side. And now, overall, we also have to balance in electrons, but in order to do that, we're going to need to multiply this reaction by 4 to get 12 electrons being given off, or lost, and this reaction by 3 in order to get the 12 electrons given off. Excuse me, in this case, required, gained, in order for the reaction to occur. So we've got 12 electrons in each case. Those must be the same. The number of electrons lost must be the same as the number of electrons gained. Those are going to cancel. We go ahead and write in these coefficients before we can forget, because that's one of the most common things to do. And we end up with the fact that 4 aluminums plus 3 tin 4 ions react to form 4 aluminum 3 plus ions plus 3 tin atoms. Double check at the end to make sure your charge is balanced. There are 12 positives here and 12 positives here on the other side. That does balance out in charges. That is the balanced chemical equation for that reaction. Now remember, these are reactions. These redox reactions are what are involved in electrochemical cells. And there are 2 types of electrochemical cells. The first is the galvanic, it's also called the voltaic cell. These are the cells that are spontaneous. They react with no outside energy input. They change chemical energy into electrical energy. And these are what we use for our batteries. We're producing that electrical energy so that we can run our toys and our electronic devices. Electrolytic cells are cells that are non-spontaneous. You have to put energy into them in order to get the reaction to occur. And at first it seems like that wouldn't be that useful, but these are the type of cells we use to electroplate metals on the surface of other metals. And so they are quite useful. We just have to supply energy into them in order to get them to work, in order for their chemical reaction to occur. In our case, we're going to spend a whole lot more time on our galvanic or voltaic cells. So remember, in an electrochemical cell, oxidation and reduction occur simultaneously. Here's a typical galvanic or voltaic cell. So we look at this and we see a cell that has 2 chambers. These chambers are called the anode and the cathode. And the anode actually is this, in this case, zinc, piece of zinc metal. As it says down here, the anode is where oxidation occurs. We have cute little ways of remembering that. Anox is the way we remember that that oxidation occurs at the anode. Over here with the cathode is actually this piece of silver metal. The cathode is where reduction occurs, and red cat is what we use to remember that and to remind ourselves that the cathode is where reduction occurs. The anode is a negative electrode. The cathode is the positive electrode. And when we set up a chemical reaction in here, electrons always flow through the wire from the anode to the cathode. And we use fat cat to remember that, from the anode to the cathode. So if you look up here, we've got this wire attached from the anode, goes into a voltmeter, the cathode, and that's the direction of electron flow from the anode to the cathode. Notice between these 2 cells is a salt bridge, and that salt bridge is incredibly important. It has to be made up of ions that can be transferred into the solution. In the case of this one with the potassium nitrate here, those ions replace the ions that are being used up or produced in the reaction. For instance, over here in the anode side, if you'll notice the arrow, this is a side where zinc is being changed into zinc 2+, which should make sense since oxidation is occurring. So we're going up in oxidation number. Over on the cathode side, we have, if you notice the arrow, we have the silver ion being plated out on the silver and turning into the silver metal. Now, that's really important because over here with the zinc, what's going to happen is as that zinc anode is turning into zinc ions, that zinc anode is going to get smaller and smaller and smaller. It's going to reduce in mass. Over here on the cathode, as that silver ion is turning into silver metal, over here, that cathode is going to increase in mass. Sometimes that's all the information they give us that lets us know which side is acting as the anode and which side is acting as the cathode when they tell us that the mass is increasing or decreasing. If they tell us that the mass is increasing for that electrode, we know that's the cathode. And if they tell us that the mass is decreasing, we know that must be the anode. So the question on the next page, maybe it's at the bottom of this. There it is. In the previous diagram, what reactions occur at the anode and the cathode? So if we look up at the anode, I'm going to actually just write them up here. At the anode, we've got zinc reacting to form zinc 2 plus. And in the process, it must be producing 2 electrons. Over on the cathode side, we've got silver ions forming the silver metal, and in the process using up an electron, which is why the electrons are traveling from the anode to the cathode. From the electrode where electrons are being produced to the electrode that needs electrons in order for the reaction to occur. In a standard electrochemical cell, there's substances are always in their standard states, and the solutions are 1 molar. To show how an electrochemical cell looks, or to represent an electrochemical cell, we use something called standard cell notation. For instance, if we had this reaction right here, then we would write standard cell notation by showing the reaction that's occurring at the anode. And remember, the reaction that's occurring at the anode is always the oxidation. The cathode is the reduction. So in this case, M is going to M plus, and they separate that with just a bar. That's the anode. The cathode then is going to be N plus going to N. They represent the salt bridge with 2 bars. If the electrode is an ion or a gas, one of the substances that's being involved in the chemical reaction, then we have to use something called an inert electrode, which is usually graphite or platinum. We don't really deal with those much at this level, so we will be concentrating more on the metal electrodes. So our example here, which is what you're going to be doing on your worksheet, is to draw the diagram of an electrochemical cell. It asks us to use potassium nitrate as our salt bridge. It says to be sure to clearly label the electrodes and the solutions that are involved, as well as the direction of electron flow. And we're supposed to show a balanced chemical equation for the reaction. Now, personally, I like to show the balanced chemical equation first, just to get started. And for me, it makes more sense when I start drawing these cells. But let's also remind ourselves, first of all, that if we have this standard cell notation, that this is the anode side and this is the cathode side. So it always is in order of how it's reacting in the reaction. So it's always going from here to here and from here to here. So we're going to write it that way. We're going to say that nickel is going to nickel 2 plus. And we're going to say that the silver ion, Ag plus, is going to Ag. And to balance that reaction, we need to balance the charge. We can do that as half reactions. On a simpler reaction like this, it's usually nice just to simply say, if I've got 2 positives on this side, I need over here, I need 2 positives over here. So if I put a 2 here to balance my charge for silver and nickel, then I'm going to need 2 silvers over here to balance by mass. Remember, we have to balance by mass and by charge. So there's my balanced chemical equation. I virtually always put pretty much always put my anode on the left and cathode on the right, but I want to make sure you realize that they don't always do that on the AP test. Sometimes they'll have the cathode on the left and the anode on the right. That's why it's critical that you remember that the anode is where oxidation occurs and the cathode is where reduction occurs. But I'm going to draw it in the same order as the standard cell notation. And remember, guys, I am not an artist, so be kind. There's solution in here. I know that in my anode, I'm going to have an electrode. I usually draw it a little bigger than was shown in the other example. There's my electrode. That's going to be my nickel electrode. And in the solution, I'm going to have Ni2+. I'm going to attach that to a voltmeter. And I'm going to draw an electrode over here. And this electrode is going to be silver. And the solution is going to be Ag+. I'm going to draw this in green because you don't have to do this, but I usually like to tell what's going on here. Nickel is, remember, going to nickel 2+, and the silver is going to, silver plus is going to the silver metal. And perhaps they might tell us that the silver electrode was increasing in mass. Maybe they didn't give us a standard cell notation, but they told us that the silver electrode was increasing in mass. Remember, that tells us that the silver electrode is the cathode. So I've got this much, but notice that one critical thing I've forgotten, because I can't have a cell if I don't have a complete pathway, is the salt bridge. So I want to make sure and label the salt bridge. Remember, they told us the salt bridge should be potassium nitrate, so that's what I'm going to label it. It's KNO3. So let's make sure and check off that we have done everything it asked us to do. It says use potassium nitrate as the salt bridge, which we did. Be sure to clearly label the electrodes and solutions involved, which we did, and the direction of electron flow. So there's one thing we haven't done yet. So let's label the direction of electron flow. Remember fat cat. Fat cat tells us it's from the anode to the cathode. So the electron flow is going to be in this direction. We've already done our balanced chemical equation, so this is our diagram of this cell.